And all of you can see my screen, right? Hmm. So today we are going to start sequential logic. So far we have been discussing various topologies of CMOS combinational logic, pull up, pull down, transmission gate, fast transistor logic and all. So today we shall do sequential logic gate discussion. As all of you know, sequential logic and combinational logic, the basic difference is that the sequential logic can hold a state. This means it's basically memory. Any sequential logic is a memory element. So what is the basic element of a sequential logic structure? The basic element, if you see the left picture, is a back-to-back inverter, inverter 1 and inverter 2. And the way they are connected, the output of inverter 1 is input to inverter 2, and output of inverter 2 is input to inverter 1. So how it works to help holding the data, this means how it works as a memory. Let's say if you follow the cursor, if the input to inverter 1 is 1, the output will be 0. That 0 goes to the input of inverter 2, so the output of inverter 2 is 1. So this means the 1 is confirmed. And same way is vice versa, right? If input to inverter 1 is 0, output will be 1. And then that output goes as the input to inverter 2, so inverter 2 output will be 0. So that also confirms 0. That's how it is holding the data. And if you see the right hand side picture, whatever is shown in the left hand side, the right hand side picture is exactly same. Only thing is that instead of using inverter symbol, we are using transistor level picture of the same two inverter back to back connection. Okay, so this is the example of um, two inverter basic bistable element. This is the basic memory cell which is present in any type of sequential cell, whether latch, whether flop. So, so the middle picture is not that important for you. So I am not discussing on that. But bottom line is that to start with sequential logic cell, the basic circuit will be back-to-back inverter. So now what we shall do a little bit of recap um, what you studied actually in your digital logic or digital, yeah, that is the previous semester, right? Digital logic class. And you know this structure. This is called SR latch. So you know SR latch, but the extension I shall do is basically how it is implemented in CMOS. Other than that, you know the symbol of SR latch, circuit of SR latch. If you see top left picture, if there is a two input, right, set and reset, the output is Q and Q bar. And below picture, you all of you know the truth table of a SR latch. When S and R are 0, output holds the value. When S1 are 0, output is set. This means Q is 1, Q bar is 0. When S0 are 1, output is reset. This means Q0, Q bar 1. And SR 1, 1 gives both output 0, 0. So that is a not allowed state. Now, this truth table, if you put in terms of state diagram, now since you have started studying finite state automata, and you have studied some of the digital logic class also, so all of you are aware of state diagram. And this picture is very simple. The state diagram of SL latch is very simple, right? You have two state 1, 0. So depending on the two input condition, right? 0, 0, 0, 1, 1, 0 or 1, 1. There is 1, 1 is not allowed. So it will be 0, 0, 0, 1 and 1, 0. How state transition happens. For example, let's say you are in state 1. If SR remains 0, 0, you will loop within state 1. So no change in the state. Same thing with state 0. You are in state 0 and SR remains 0, 0, then you loop within the same state, no change. But you will go from state 1 to state 0 if SR is 0, 1. You will go back from state 0 to state 1 if SR is 1, 0. So this is how it looks. Basically, state diagram is a graphical representation of the truth table or state table. Now, if you see the CMOS implementation, basically what we have done, we have take it's basically two NOR gate, right? And since it is two NOR gate, what we have done is um, each NOR gate we implemented in terms of two input CMOS gate, right? So you know that for two input NOR, NMOS in parallel, PMOS in series. So this is one NOR gate if you see the cursor. This is the other NOR gate, and there is a back-to-back connection, right? One output goes to others input, crisscross type of connection, which you can see in the circuit. So conceptually, all of you who are aware of special latch, so it will soon clear to you why I am taking this approach to discuss about the sequential cell. Particularly, we shall be discussing the industry standard latch. So now the interesting thing is that we are interested in clogged SR latch. We are still discussing the NOR version of SR latch. Clogged SR latch means you added another two input AND gate. So the idea is that one input of the AND gate is clock, other input is S for the upper AND gate. For a lower AND gate, one input is clock, other input is R. So as it is very obvious in the circuit, when clock equal to 1, then this S goes to the output, right? And the same way, this R goes to the output. This means now this whole circuit can act like a regular SL latch. But if clock equal to 0, then the both AND gate outputs are 0, right? No matter what is the value of S and R. So 0, 0 means output will hold the state. So this is called clocked SL latch. So I'm not going to the waveform detail right now. You can study yourself. So continuing on that, I want to make D latch using this clogged SL latch. Okay. So if we want to make D latch, so why I want to make D latch? D latch means data latch and clogged data latch. This means in industry, whenever we talk about any latch operation, it always has to be clogged. Okay, it has to be synchronous with clock. So clock is a important primary pin for that particular circuit. So if I want to implement a data latch using clogged SL latch, then we can do it by one simple change in this circuit. I'm sure you have studied at least something about it in digital logic class. And the solution is simple, right? What you do, you take the S input, put in inverter, and the inverter output will act like a R input to the circuit. You see the remaining circuit is a clocked SL latch. So now, by this special connection of this inverter, we now introduce the data input, right? So that will make it CMOS data latch. So the idea is that when clock equal to 0, then both AND gate output is 0, output will hold the state. When clock equal to 1, then data will go through that S type input and data bar will go to the R type input. This means what? When data is 1, Q will be 1. When data is 0, Q will be 0. So this is just basically the truth table or algorithm of a simple data latch. And the algorithm is as simple as this. When clock is 0, output will hold the value. When clock is 1, whatever is the input data will be reflected in the output. Tell me.
Sir, what is the function of this inverter?
This inverter, what it is doing, let me go back to the previous. See, you have the S and R, right? And now once we put the inverter, what we are doing, this data, S is now data, and this D input, and the data bar, which is that the output of inverter, is your R. This means now for this particular circuit, the relationship between S and R is like that when S1 R0, when S0 R1. So now if you look back, when S1 R0, always Q is 1. When S0 R1, always Q is 0. This means with that particular inverter, the circuit work in a way so that only these two states are possible when clock equal to 1. This means whatever be the data will go to the output. Okay, that is the importance of putting inverter. So in traditional digital electronics, this is how we implement data latch. Now, why I am talking about data latch? Basically, there are varieties of latches in industry, but the most common, the most popular one is data latch. There may be various flavors of data latch, but this is it. That is why I am teaching data latch. This is the most popular sequential cell used in industry. Okay. Now, let's do a count of number of transistor if we implement all these gates using CMOS. Now, what we shall do if we convert each NOR gate, AND gate, inverter by CMOS, then let's see how many transistors we have. If you see this two input NOR gate, each two input NOR gate has 4 transistors, 2 PMOS, 2 NMOS. If you talk about each AND gate, it's basically NAND gate followed by inverter. So 2 input NAND gate has 4 transistors and the inverter has 2 transistors, so total 6. And inverter has 2 transistors. So now if I add all these transistors, 4, 4, 6, 6, 2, this means total 22 transistor. Now, if we implement 22 transistor based latch, then the number of transistor will be too much because there are millions of latches in a high-end processor, right? So, if each latch itself take 22 transistor, then how we can cope up with the demand of transistor, right? So that will be too much. It will cost too much power, area, timing, whatnot, right? It has big impact on circuit. So then technology started thinking how to reduce the number of transistors drastically. Still, it will function like our traditional data latch. Okay. So they took a different approach, and the approach is more towards fast transistor logic or transmission gate logic, which I explained you in the earlier classes. So let's see how we can reduce the number of transistors using a little bit of different topology. So to start this discussion, why not we take a very simple circuit with a single NMOS. This is your pass transistor logic. I already discussed with you how pass transistor logic works. It's a single NMOS. You have input, we connect to data, output connect to Q, and the gate is connected to the clock. As you all know, I just explained also the algorithm or the basic truth table of a data latch is that when clock equal to 1, input data will go to output. When clock equal to 0, output will hold the state. So let's see how it works in this case. As you all know, for a CMOS circuit, whenever we have all this connection, there is capacitance, right? C1, C2 coming out of driver cap, wire cap, receiver cap. So capacitance is always there. Now what is happening when clock equal to 1, this NMOS transistor is on. Since NMOS is on, the data will simply go to the output. Okay, so that will be your Q, right? And when data 0 is same thing, right? Logic 1 passes, logic 0 passes, fine, no problem. But when clock equal to 0, you see this transistor becomes off, so this Q will become floating, right? So it will try to hold its previous state. So that way it is satisfying the logic of a latch. But circuit wise, it has 3 key problems. And what I shall do now, ideally speaking, one transistor is good enough to implement the logic of a latch. So whatever we have been trying out with 22 transistor in the previous picture, the same thing now implement with one transistor. It looks too optimistic. Something somewhere there is problem, right? So we shall now discuss some of the circuit problem with this. But before that, one interesting point I want to share, that when we make extremely high density memory arrays, right? You know that, everywhere memories are used, right? On chip memory, standalone memories. So this is a typical memory which is extremely famous, and all of you probably know this type of memory is called DRAM. So this is like a one DRAM cell, one single transistor with a capacitor, and it is, since being a single transistor cell, the density of DRAM array is extremely high, and this DRAM array popularly in computer is called your main memory. As all of you know that main memory is not part of your CPU, right? It is a separate standalone memory in the motherboard, right? And CPU communicate with main memory. All of you have taken, I'm sure, some computer organization or architecture class, so you know how memory interface works and it interacts with the CPU, right? But physically, this is like one transistor memory called DRAM. And today, if you see market DRAM is available like 4 GB, 8 GB, 16 GB kind of sizes. So it's a huge number, right? So, but that is there, right? I just told you about it because it's one of the key application of semiconductor and is very much relevant in today's in electronics. But this particular circuit has few issues. What I shall do, instead of telling all the issues together, I shall tell you one by one issue and how it is solved. And you will see while solving these issues, we are gradually increasing number of transistors. But at the end of the day, our goal is still to keep minimum possible number of transistors and still make the circuit robust. The first problem is, it's all circuit problem, right? The output can only rise to VDD minus VT. So this is a typical fast transistor problem. I discussed about it and explained to you in the previous classes that when I try to transfer logic 1 to NMOS, it is always weak logic 1, because input logic 1 means VDD, output can maximum go to VDD minus VTH, right? I already discussed with you in details. So the logic 1 transfer is weak. So that is the problem. Okay, so how to solve that? In order to solve that, all of you know what we did, we introduced the concept of transmission gate, where not only NMOS, we also connect a PMOS with clock bar at the input. So this is the concept I discussed with you before. So now the first problem gone. If you introduce, instead of pass transistor, a transmission gate type of logic, NMOS connected to clock and PMOS connected to clock bar, then yes, all the logic problem is solved. That when D goes to Q, it is healthy logic 1 and it is always healthy logic 0. Now comes the second problem. If you see this particular circuit, the output has only Q. But what we want is also Q bar. Any latch has both Q and Q bar. All of you know that, right? In a traditional latch, always there is Q bar. So Q bar is missing. So how to introduce Q bar? It's very simple, right? You simply put an inverter next to Q. The moment you put an inverter next to Q, you get Q bar. So the second problem is also solved. Now you can see that we are solving all these circuit problem one by one and gradually increasing the number of transistors. So now in this circuit, there is already one, two, three, four transistors. So we started with one transistor, and while solving the circuit problem, we are increasing number of transistors. Okay. Now comes the last problem, which is the most difficult one, that is noise problem. See, what is happening is that the value that we are storing in Q, right, in this memory element, 1 or 0, right? When the clock is 0, right, or clock bar is 1, then both NMOS and PMOS are off. When both are off, then we are trying to hold that data in Q. Okay, now what will happen? The Q can easily lose the charge. Okay, so there is no way Q is connected to VDD or ground, so Q is completely floating. And when Q is completely floating, this means it is in high impedance state. I told you before, right? Floating state, high impedance state, they are all synonymous, right? So when Q is in high impedance state, then what happens? That the charge that it is holding or the voltage that it is holding, it can easily get discharged. Okay, so it's a noise problem. So how to solve noise problem? This is the last problem. We have to make sure when memory is holding the data, clock is 0 and the data hold is strong. The data hold is not weak. Okay. So to solve this noise problem, this is the circuit what is done. You have already seen that this Q bar, there's an inverter in between. So now we introduced another inverter called inverter 2. And that output of the inverter is now connected back to Q. Okay, so this is pretty much the circuit that we are now introducing, and we are claiming that this circuit will solve the noise problem or the floating note problem. So I shall explain you in more details how that happens. But this extra inverter that we introduce now is called keeper, and it also causes another circuit problem called contention. So I shall discuss all these step by step. I have a couple of nice pictures so that you can understand easily. But the idea is that high level you can see right now the connection is something like back-to-back inverter. So you started with Q bar and you come back to Q. So I told you at the very beginning, whenever you have this back-to-back inverter structure, this is our typical memory element. It helps to hold the charge. So now what I shall do, the same circuit, I shall draw in a slightly different fashion with transistor level picture, and I shall explain you step by step how this particular configuration is, is going to solve the noise problem and will hold the charge strong when the clock is 0. So this is the type of circuit which is extremely popular in industry, particularly DLATCH is extremely popular in industry, and that is why, keeping the big application in mind, I am teaching this particular circuit. So now let's start with this, circuit. So idea is that this is nothing but the previous circuit. So let's compare, right? This is your D input and the Q output, right? So this is what is D input, Q output. Then you had inverter 1 and inverter 2. So this is your inverter 1, and I have drawn the inverter 2 in terms of transistors. And it will be very clear to you why I have drawn inverter 2 like this. It's basically the same circuit, no difference. And in order to complete the discussion, I have introduced another inverter at the input, because you see the D will come from some CMOS circuit, right? D just cannot come as it is, right? So in reality, there will be always some CMOS driver, right? That is why I have drawn that inverter for the completion of circuit. So now this is your actual transistor level implementation, and follow carefully how I am going to explain this circuit which will fight the noise. Let us start that with the case that we want to solve the noise problem, right? So definitely the clock should be 0, right? The expectation is that the circuit will hold the value when clock equal to 0. That is the basic latch operation. So clock 0, and automatically clock 0 means the corresponding NMOS is off. Now clock bar is 1. Naturally, if clock 0, clock bar has to be 1. So that will also make your PMOS off. So if NMOS off, PMOS off, there is no way data can go to Q. So the Q is now totally isolated from input data. Now see what happens. Let's assume that the value that it is trying to hold is 1. So the value it is holding 1, and that will make Q bar 0 because it's an inverter. So if Q bar is 0, now see what is happening. The NMOS for this inverter is off, and the PMOS for the DC inverter is on, right? So that creates a very interesting voltage situation. What is that? That is, you see the Q, which was holding 1, is now connected to VDD through this PMOS transistor. So now Q is getting strong connection to VDD. Previously it was just floating, but now it is not floating anymore. Q is connected to VDD through this PMOS transistor. So this means if there is any circuit noise, let's say down glitch, right? It is holding 1, some glitch comes. So in circuit, the noise is always in form of glitch. Now, when the glitch will appear through various reasons, what will happen? This PMOS is on, right? And Q is connected to VDD by PMOS, so PMOS will fight. PMOS will fight this glitch and will ensure that this output Q is always strong 1. So this is the job of this PMOS transistor. It is called keeper. So keeper should be strong enough to fight this noise. This is the whole philosophy by which this keeper transistor work. Okay. Now, the more you make this PMOS strong, so how you can make PMOS strong? If you increase the width of the PMOS more and more, it will be more strong. The more strong you make, it will hold the value 1 easily. Okay. So now this thought process that I explained to you, you yourself should do the same thought process in your own way. If you hold value 0, then you will understand the entire thing. So I told you the half portion, the other half portion you yourself need to think. It's very easy. It's the same approach. So this is how keeper actually helps to fight the noise. Now, okay, this is all good. So what is the problem with this circuit? See what happens, there is no free lunch, right? Any goodness we try to introduce in a circuit, some other parameter gets distracted or get disturbed. So always there is a trade-off, right? This is why it is engineering. There is never a perfect solution. So far, what we have done, we have increased 2 more transistors, right? 1, 2, 3, 4, and now 5, 6, right? So 6 transistors. Now, this circuit is very good for noise. I already explained. What is the problem with this circuit now? The problem is with delay. So let's again discuss in the same animation way so that you understand easily. Solving noise problem is now introducing the delay propagation through this circuit. So let me explain you how it introduce delay issue. So what happens? We are starting with the same case. Is that now we shall make clock 1. So the NMOS is on, clock bar 0. So the PMOS is also on of the transmission gate. We were holding Q equal to 1, right? So it's the same example I'm continuing. So we are holding Q1. Now we made the transmission gate on. So let's see what happens. Same thing, right? Q bar 0, PMOS is on, NMOS is off. Exactly like the previous example. Only difference is that now I have made the transmission gate on because I want input data to propagate to output. So now what happens? Let's say I apply input transition 0 to 1, NMOS on, that will make PMOS off. So this D will now try to go down, right? It's an inverter, right? So D will try to fall. So when D will try to fall, the transmission gate is on, so that fall will get transferred towards the other side. So Q will try to fall. So now the problem is that, see carefully what is happening. This PMOS is on, these 2 transmission gate transistors are on, and this pull down NMOS is on. So you can see there is a direct path traveling like this: VDD, PMOS, transmission gate, NMOS, and ground. Okay, so this is called contention. There is a direct path from supply to ground. So you start with VDD to on PMOS, to on transmission gate, to on NMOS. So all the transistors are on from VDD to ground. As a result, what will happen? This Q will try to fall, but this PMOS will not allow it to fall. It is fighting. That is why it is contention. So if it is more, it is fighting, the Q will have more difficult time to fall. So this means there will be timing push out. So this is the problem when you have the keeper. So this will cause delay problem, which will ultimately impact your performance. So how to solve that? In that case, if you want a good delay transition, then definitely you will try to make the PMOS weak. So if you can PMOS weak, make the PMOS weak, then the fight will be less and the data will go to Q more easily. The delay will be faster. Okay, so what we got from the previous discussion, we got that for good noise, this keeper has to be as strong as possible. And now what we discussed, for good delay, this keeper has to be as weak as possible. So now it becomes very important how we design this keeper transistor. Okay. Now, if we can do proper sizing of this keeper transistor, then definitely we shall be able to come up with the best solution trading off between noise and delay. So, so this is how this circuit works. This is actually very, very popular in industry. See, we are doing with 1, 2, 3, 4, 5, 6 transistors. If you compare with the original 22 transistors, it's only 6. So that is, way more than 50% reduction in transistor count. But you have to be very, very careful with the sizing of the keeper. If keeper is strong, good for noise, bad for delay. If keeper is weak, good for delay, but bad for noise. So you need to do a lot of simulation and sizing. Now, we can eliminate this problem also completely to make it 100% robust data latch. That we can do, but again, we shall introduce a couple of more transistors. See, every time we are trying to make the circuit more and more robust, the only problem is that we are increasing number of transistors. So now, let's see how we solve this delay versus noise problem completely, and for that, this is the circuit. So in this circuit, see this D, Q, Q bar, this structure is still the same. Now in this feedback loop, what we have done, we have introduced another transmission gate here, right? And the speciality is that the input transmission gate, if it is clock, NMOS is getting clock. In the feedback transmission gate, NMOS is getting clock bar. In forward transmission gate, PMOS is getting clock bar. In this feedback transmission gate, PMOS is getting clock. So it's the clocking is exactly opposite. And as the clocking is exactly opposite, now what is happening is that when this input transmission gate, the switch is on, the feedback transmission gate of the switch is off. When input transmission gate switch is off, the feedback transmission gate switch is on. So this is pretty much what it is. So this becomes, with this new structure, this is called interruptible keeper data latch. So if you now go back to the previous picture, the difference is that what we have done at the output of this inverter, here we have put another transmission gate with opposite clocking. Okay, this is exactly where, if you follow my cursor, here we added that extra transmission gate, which is this one. Okay, now the operation is very clear. So now let me explain. So this type of configuration is called interruptible keeper. So it will be very clear why it is called now interruptible keeper. Because, follow carefully. Let's say when the latch is on means clock equal to 1, clock bar is 0, the switch, the input switch is on, right? You can see it's like an on switch. So this picture is more like a symbolic picture. It makes the whole circuit very easy looking. And you see there are, these two inverter, right? And the feedback transmission gate is now off, right? So this switch is open. So equivalent circuit is something the data is coming and straight away going to output Q, and when the clock equal to 1. Okay, so this is 50% of the operation of latch. What happens when clock equal to 1? Data simply goes to the output. Okay, and absolutely there is no contention. The delay is best. This is very good. Now let's see the opposite scenario. In opposite scenario, what happens when clock is 0? Input switch is now open, but the feedback switch is now closed. Now how it is working? Input switch open, so the data cannot go. It is completely cut off. But now since the feedback switch is closed, this two inverter is now acting like a back-to-back inverter, which is a basic memory element. So it is holding the data. So as a result, what is happening? This circuit is working very good to protect against noise. But since the input data is cut off, absolutely no problem, right? So this is how this circuit is solving both noise and delay problem. So when clock is 1, feedback switch is open, So data nicely goes to queue, no delay problem. When clock is 0, then feedback switch is closed, input switch is open. So this back-to-back inverter is now active, so it can nicely hold the data. So no noise problem. So only penalty that we gave, now we have 1, 2, 3, 4, 5, 6, 7, 8, 8 transistors. This is called interruptible keeper configuration, which is the most robust version of latch. Okay, and this is so popular in industry, as I told you, right? The data latch is basically the most popular latch, and interruptible keeper data latch is the most popular configuration. Now if you compare to the original latch that I told you, 22 transistor, finally we got extremely robust latch with 8 transistor. Still it is much more than 50% improvement. This is why transmission gate based uh, latch is so popular in industry. So now this is the operation I just told you, right? When clock 1, what happens? When clock 0, what happens? When clock 1, data simply goes to output, no delay issue. When clock 0, output is held by this back-to-back inverter. You can see the feedback path is closed. So now I shall give you a simple definition called setup time and hold time. So if you see this particular latch, what is happening when the clock is transitioning from 1 to 0? So before that, clock was 1, so data was going to output. After that fall transition, clock becomes 1 to 0, then the output is holding the data, right? Data is unable to go. Now, this is how, so this edge, the falling edge of the clock is called capture edge. The example of the latch I am discussing is called positive latch, because this particular latch is open, is on when clock equal to 1. And you can also see this is level triggered. Level triggered means when clock is 1, data goes. When clock is 0, output is held, right? So this type of configuration is called level triggered. Any latch is level triggered. And in this particular positive latch, it is called positive latch because when clock 1, then only data is allowed to go to output, which is why it's called positive latch. So the critical edge of the clock is the falling edge, because before falling latch is on, after falling latch is closed. So what is happening with the falling edge of the clock? You see the input data needs to be stable before some time from the falling edge of the clock, and that is called setup time. Same way, input data has to remain stable after falling edge of the clock, that is called the hold time. So that is why you see this is more like, this type of waveform you have seen a lot in your microprocessors. In this picture, the idea is that you can see how the data waveform is drawn. There is gray area, there is white area, there is gray area, there is white area. So white area is the area where data needs to be stable. Okay, it has to be valid. It has to be stable. The idea is that data has to be stable sometime before the critical age of the clock, in this case falling, which is called setup time. Data has to be stable after some time from the falling age of the clock, which is called the data in the hold time. And if you see, if you add setup time and hold time, these two together is basically your white area. This means this is the window where input data has to be stable. The question is that why there is setup time and hold time exist? And the answer is very simple, right? All these digital gates or the transistors that we are using, they all have finite delay, right? Since they have finite delay, automatically, data needs to stabilize before the clock fall, and it needs to be stable after the clock fall because of finite delay through all these elements inside the latch. So as per your course, the definition of setup time and hold time is there. So that is why I explained that. And this setup time and hold time is the critical property of any sequential element. If you see any combinational logic, we never discussed about setup time or hold time. Okay. So the next topic is flip-flop. So what I shall do, I think if I start flip-flop, we shall run out of time. So why not I continue the flip-flop discussion in the next class? and then I shall enter the last part of module 1, which will be physical layout design. And by the way, I have posted 2 volumes, EDA volume 5 and 6, which contains all these information and slides. So this is what I discussed today. Sukarna will take care your this thing, attendance issue. Okay, Sukarna is there. She is taking care of the attendance and working with me, so there is no problem on that.